Okay, so we're on our last outcome of this unit already. So it's a really quick one. This is lesson 5.2, graphing linear inequalities in two variables. So up until this point in this unit, we've seen linear equalities in one variable, so just dealing with x. We've also seen linear equations, and we've kind of refreshed our memory on how to graph those when we were dealing with systems of linear and quadratic inequalities. So now we are looking at linear inequalities in two variables. So a linear equality in two variables in general form looks like these. So the key thing to note about general form is that it's all set to 0 or compared to 0. Unfortunately, this is not ideal in terms of graphing. So things to remember is that we will eventually want to isolate y in order to graph. Okay, an inequality in two variables, x and y, describes a region in the Cartesian plane, aka our normal grid. Let me get a highlighter for that. Cartesian plane is referring to our normal grid. So that's this guy here. The ordered pair x and y is a solution to an linear inequality if the inequality is true. Okay, and so remember, true meaning that it keeps that meaning of those signs to be exactly what they mean. So greater than, so that means that this number on the left-hand side has to be greater than 0 when the values of x and y are substituted into the inequality. The set of points that satisfy a linear inequality can be called the solution set or solution region. Now you'll notice that this is different than our systems of equations where they had a defined point. The solution was one exact value or maybe two exact values. Here we're going to have a range of values because we're dealing with an inequality, so it could be anything within a range of data. So thinking back to our first couple of lessons in this unit, we would isolate our single variable and we would say that x could be, for example, greater than 5. That means that any number, no matter whether it's 1000 or 5.001, would satisfy that solution. So that's the whole solution set or solution region. Here we're dealing with the same thing, but we're dealing with 2 dimensions at a time. So that's where it gets a little interesting. So part 1 of our solution is our boundary. Okay, the boundary is our line or curve, once we get into quadratics, that separates our Cartesian plane into 2 sections. The section that is part of our solution set and the section that isn't part of our solution set. This follows our equation. So this is why we're going to want to isolate y and create a y equals mx plus b sort of look to our inequality so that we are able to plot this line more effectively. Okay. A solid line is kind of like a filled in hole on our number lines from that first outcome that we did. Okay, so a solid line is used for when it is potentially equal to. A dashed line or dotted line means that it's not equal to. Okay, so that's part 1. So let's have a look at what this actually kind of ends up looking like. So it says graph 2x plus 3y is less than or equal to 6. Use the intercepts to graph the line. Select a test point from each region to determine which contains the solution. Okay, so use the intercepts to graph the line. So that's another option we have. If we don't want to isolate y, we can just plug in 0 for x and y and find our x and y, or y and x intercepts. So to solve for my x-intercept, this is for part A, that means that y needs to be 0. So I'm going to plug in 2x plus 3 times 0 is less than or equal to 6. Well, that goes away because anything multiplied by 0 is itself. So we've got 2x is less than or equal to 6. That means that x is less than or equal to 3. So the key idea is that 3 then becomes my equal to point. It's my x-intercept. You could also change this to be an equal sign just to treat it in order to solve for your x-intercept. I'll show you what that looks like with the y-intercept. X needs to be 0. So we're going to be working with the idea that this is actually a function, not an inequality. And so we'd say 2 times 0 plus 3y is equal to 6. So we're allowed to do this because we're strictly solving for a specific point. We are not talking about the function on the graph. Okay, so when we go to graph it, we still need to go back to that original inequality that we were given. This goes to 0, so y is equal to 2. So okay, I've got my x-intercept, I've got my y-intercept. I'm going to put that on my coordinate plane here, or my Cartesian plane. I'm going to maybe put my x-axis a little bit lower here because I'm dealing with all positive values. And again, I'm going to label my scale. This is 0. Okay, you'll notice that I'm not actually like outlining the whole thing. It's just because my marker is not as thick enough. So I'm just going to make defining marks so that I can kind of keep track of where everything is. So I need to go, x is 3 and 0, so right here. Y is 0 and 2. And so that's going to be my line. Now, before I actually connect those points, that's when I need to decide, am I drawing a solid line or a dashed line? I look at the inequality symbol here. It's less than or equal to 6. So what I'm going to do is I'm going to do a solid line because it can be equal to. Okay, and so there we go. I've got my line. It's solid. I'm not quite done yet though because I have to do part B. I need to test points to determine which ones contain the solution. So I need to see if it's a point from above the line or below the line that is going to make my inequality true. So my point below the line, I'm just going to use 0, 0 because that makes my life easy. So point 0, 0, if I test that, it's 2 times 0 plus 3 times 0 is less than or equal to 6. 0 is less than or equal to 6 is a true statement, which means that below the line is going to be valid. If you want to double check to make sure you didn't just make a calculation error, you could choose another point above the line. I usually like to use another point on my axes, just personal preference, because then I still get to use 0 a little bit. So I'm going to use this point here. This is point A. Again, this was point P. So point A is 2, 3, 4, 5, 6, y, 0 and 6. So 2 times 0 plus 3 times 6 is less than or equal to 6. That's 18 is less than or equal to 6. That is not true. So I know that my solution region is below the line. How I show this is I'm going to shade below the line. And there we go. It might be more effective if I use a highlighter, but whatever works for you. If you do just like diagonal lines, that would be fine as well. Okay, but shade in a manner that signifies anything below that line is going to work. Because it's not just our line with this inequality, it means anything below 6. So that line represents where kind of 6 is. So those are your two steps to graphing an inequality. You want to graph the inequality as if it was an equation, decide if it's dotted or solid line, and then shade the rest of the solution. This is option 1 for checking where your solution set is. I'll label it in the question. Now, my personal preference is to do it slightly different, but again, that's really just me. You don't need to do this. You can keep with that method that we saw in the previous example, but I'll show you just in case it's up your alley as well. What I like to do is I don't like working in general form. I genuinely think it is not as helpful as I would like it to be. So what I like to do is I like to rearrange so that I have y by itself, so it looks like y equals mx plus b. I find this is the most effective form of graphing a linear equation. Again, just personal preference though. So what am I going to do? I'm going to move my negative 5y onto the other side since it's equal to 0, so it's going to be positive 5y. And I'm going to divide by 5 to isolate y by itself. So I get y is greater than, or sorry, y is less than 2x. This is easily graphed. My y-intercept, my b value, is 0. It's non-existent. My slope is 2, so rise over run, that would be 2 over 1. And so now I'm ready to graph my line. So both take about the same number of steps. I genuinely just prefer my slope-intercept form for graphing. Label your scales, label your axes. Negative 1, 1, and here we go. So my intercept is at 0, 0. I go rise of 2, run of 1, rise of 2, run of 1. And I can define a bunch of points that I'm going to connect. Okay, it is not equal to though. Y is less than not equal to my equation, which means that I'm going to draw a dotted line, which is nice for me because then it might actually resemble a straight line. Maybe not. Okay, we still put arrowheads on the line because it still can go on forever. So I've got my dotted line. Now what's nice about this statement is that y is less than my function. That means that it's already telling me where to shade, and I don't need to test points except to maybe verify. So here it's saying y is less than the function. Well, that means I'm going to shade below my line. Where is below my line? Well, if I find any point on my line, I'm going to go down from there, which means it's all this side. So that's my personal preference as to how to decide where to shade. I like isolating y and going from there. If you like that previous method where you just pick 2 points, plug them in, check to see if it's true, you can do that too. Totally welcome. I'm still going to double check that I'm right by using a test point. So I'm going to choose, again, something on my axis so I can still use 1, 0. And I'm going to plug it into the original equation. So I'm going to choose 2, test point 2, 0. That's 5 times 0 is greater than 0. 20 minus 0 is greater than 0. That is true, so that point is valid, and I know I've shaded the right side. But this is just verifying. Okay, so working backwards. Can you write an inequality to represent the graph? How I like to do this is step 1, write an equation, and then just tweak it based on your kind of dotted or solid line and where it's shaded. So again, I love me my slope intercept form. So we're going to see that here. Our intercept is at 1. my slope is, from here I go up 2 over 1, so 2 over 1, remember rise over run, which is just positive 2. So those are my two values. So if I was writing an equation, it would be y equals 2x plus 1. But I'm not writing an equation, I'm writing an inequality. So I notice that I'm shading above my line. If I find a point on my line, I have to go up to get into my solution set. So it's going to be y is greater than, not equal to, because it's a dotted line, 2x plus 1. That is going to be my solution. If you are asked for it in general form, what would you do? Well, you would just move your y over onto the other side, or move your, because we always want our x to be positive. So you'd have 0 is greater than 2x minus y plus 1. Okay, so this is in general form. Let's try again. Write an inequality to represent the graph given here. Same process. My y-intercept is at -2. My slope is actually down 1, or down 2 over 1. So rise is -2, run is still 1. When we're determining our run, always go from left to right, just good convention to make sure that we don't mess up our signs. Okay, so we go down 2 over 1, -2 divided by 1 is -2. It's going to be possibly equal to, because I've got a solid line. From my line, I would move upwards, so y is going to be greater than or equal to -2x minus 2. If I wanted to put this in general form, because I always want my x value to be positive, my coefficient to be positive, that means that this is for general. That means that I'm going to rearrange it so that I've got 2x plus y plus 2 is greater than or equal to 0. So in this case, I moved everything on the right-hand side over to the left so that I could change that sign of my x term. So the key thing here is I'm going to try and add and subtract as much as possible in order to eliminate negatives, because as we saw in our second lesson of this unit, in our first lesson of this unit, if we divide or multiply by a negative across the board, that also flips our inequality sign. So the less I have to worry about that piece, the easier it makes my life. So I'm going to try and do that as much as possible. Example 5, we've got a word problem, because that's where these inequalities really fit, is describing real life situations. Most of our equations describe one specific path. This inequalities allow us to describe any number of scenarios that fit a specific set of parameters. So that's why I like this unit. It's applicable. So suppose that you are constructing a tabletop using aluminum and glass. The most you can spend on materials is $50. So I already know that I have a maximum of $50. The laminated safety glass costs $60 per meter squared. Whew, that's a lot of money. And aluminum costs $1.75 per foot. So odds are I'm going to be using more aluminum than I am glass. You can choose dimensions of the table and the amount of each material used. Find the possible combinations of materials sufficient to make a tabletop. So while we're looking at this, we need to write an equation. That's the first thing that we would need to do. So we would start by saying, okay, well, this is great. This is my maximum, so that's going to be kind of by itself. That's what everything needs to add up to. It's got to be greater than or equal to. Everything else has to be less than $50 or at the most $50. So I'm going to send $60 potentially per glass amount, and I'm going to spend $1.75 per aluminum amount. So now I've got my two variables, amount of aluminum, amount of glass, which means I'm working in the same realm as all the rest of this lesson, and I'm comparing it relative to 50. From here, you can use either strategy you want in order to put this equation on the graph. Again, I like getting my variables by itself and making it look like y equals mx plus b. So I am going to do this. I'm going to say aluminum is my independent, so I'm going to get 1.75 by itself. It's less than or equal to. Now, you'll notice I flipped that sign, but I've also flipped where this is. Okay, if that doesn't make sense, keep everything kind of where they were and just move the 60 onto the left. Okay, so I get that, divide by 1.75. Okay, so this is where my y equals mx plus b might fall apart because I'm dealing with all sorts of crazy decimals. So you might want to use our other strategy of finding our intercepts. So you'll see I've solved for my y equals mx plus b form, and I set my a variable as my dependent. So I did the same thing over here, and I did the intercept method as well. So in that case, a or my y-intercept would be 28.57, so that kind of jives with this. And then I got my x-intercept, aka g, to be 83.3. So when I go to graph this, oops, sorry, that's not 83.3. That wouldn't make much sense. It would be 0.833. I didn't think that was logical. So based on that information, I'm not going to put 1 as my y-intercept here. Okay, I'm going to graph G and A, not X and Y. You'll notice I'm only doing quadrant 1. That would be because I'm not going to have negative measurements. I'm not going to return extra aluminum to get glass. That's impossible. It's not what I'm doing. I need to use both materials. So I can't go outside of the first quadrant. From here, I'm going to go up maybe by 2, let's go by 4s. So 4, 8, 12, 16, 20, 24, 26, oops, 24, 28, and so forth. 32 is the next one. Here I am going to, you know what, maybe I could go by 2s here. Okay, so choosing your scale is very important. 4, 8, 12, 16, 20, 24. Yeah, I can fit 28 in here. Excellent. Horizontally, I'm actually going to go up by 0.05. So I'm going to have 0.1 here, 0.2, 0.3, 0.4, 0.6. Oh no, I'm going to run out of room for that. So again, we change our mind, and maybe we go up by just 0.1 every time. 0.2 is this guy, 0.4, 0.6, 0.8, 1.0, and so forth. Okay, so I got some good axes now. I can be confident in my decision because I've changed them around. The reason that I'm being so fussy about my axes is I want a decent picture of what this graph looks like. And if I had just put 1 right here, well, that line would barely fill this space. And what would be the point of having such a big grid? So the better picture I can get, the better off I'm going to be in the long run. So use your scales smartly. So I need to go 28.57. Well, it's going to be just above 28 there. Put that point here. My other intercept is going to be 0.83. So I'm looking and I'm like, okay, well, that's going to be maybe here-ish. And then we're going to connect those lines. And this might take it. Oh, did a pretty good job. Oh, yeah. Now, I can do a solid line here, so that's kind of nice, because I can spend $50. That is my maximum, but I can spend it. So it's inclusive, equal to. Now the question is, can I spend more than that value or less than that value? So again, we can test some points. I like to use the origin wherever possible. So I'm going to verify. 0.00 works. I'm going to plug it in. 0 here, 0 here. 0 is less than or equal to 50. That is true. So I can say that my solution set this section here. So you are not done dealing with inequalities in two variables until you have completed this graph, including the shading part. If you don't complete the shading, you are not done because you've just represented a couple of the values, but the shading represents all the possible values. So I could choose technically a point like here, and that would be a valid solution. And in this case, because we're talking about measurements, I could totally choose a random measurement, and that could potentially be what I'm buying, depending on how they actually vend those materials. So that's kind of how this all shakes out. So my solution is my graph. This guy right here, that's my answer. And I'm done. So we've got some practice questions in our work text. You definitely want to have a look at some practice questions. Make sure we're comfortable with this because our next lesson is working with quadratics and inequalities. So bringing it all together. So good luck, and we'll see you in 5.3.